Welcome to Applied Bioinformatics. In this video, I will show to you code that implements neighbor joining. You have hopefully watched already the video on hierarchical clustering. So now we copy more or less the same code and extend it to implement neighbor joining. So the key difference is that besides the D matrix, we also have a Q matrix, and we're going to see in a minute what we're doing with that. We consider here in this example 4 nodes, A, B, C, D. You can easily expand that, make it FG to have more. But for the sake of simplicity in this example, and this is a video, let's leave it at 4 nodes. A few libraries are needed, random for random number generation, networks for the layout of the tree in the end, and for that we also going to need matplotlib. And as I said already, lots of the code is copied over from hierarchical clustering. So here's some useful stuff that is really just on the side. Label is ordering the nodes, so if we have A and B and alphabetically A is bigger than B, then the order is swapped, so that we have basically a new way of putting A and B into the distance matrix. Then we initialize the distance matrix by randomly generating values between 1 and 100. We have code to nicely print out the labels 2 different ways for 2 different purposes. And we have here a very long function, print matrix, that is using matplotlib's table environment to print out the distance and the Q matrix in a nice way. So this is long code, but it's not really that complex. It requires kind of lots of functions to set, for example, the background color, the font, the sizes, and so on, so that it all looks beautiful and nice. But then we come really to the heart of the code. This is really where the action is, and the very heart of the code is this while loop. This was in hierarchical clustering in the most basic version, 12 lines that implements hierarchical clustering. It's a few lines more now, but the principle of the code remains exactly the same. The biggest difference is over here in the choice of the minimum. In hierarchical clustering, the minimum was simply taken from the distance matrix. The 2 nodes with the smallest distance to each other were considered the next pair to be clustered. We identified a disadvantage in this approach in that the choice is made locally, not considering the distances to all the other nodes. And for that we introduced neighbor joining, and the key was the computation of the matrix Q. And for that we have here the method getQ, and let's have a look at what getQ is doing. It is creating an empty dictionary to store the matrix that we want to compute, and now it's visiting all cells in that matrix A and B, and we're checking first of all whether A and B exist in our distance matrix, and if that is the case, then we're computing the Q value for these A and B. And you can look it up in your slides. That was a formula, and essentially this was n minus 2, and n, that is the number of nodes we have, so the length of the list all. So n minus 2 times the distance between A and B minus u of A and u of B. So u of A and B we have defined over here. So it sums up all of the distances from A, and with list comprehension, this is beautifully programmed in Python as follows. We compute the list over, the sum over the list of all of the corresponding entries in the distance matrix, and A was given, so we essentially have to iterate over all B, so all B in the list all, so all nodes that are present. And just to be on the safe side, we're checking that the entry AB is in fact in the distance matrix, because if we don't do that, it would give us an error if that value was not present. So collect all those entries from the distance matrix that have A in them, and then sum it all up and return the value. So this is being processed here, and that's exactly the function as you know it from the lecture. In the lecture we had it written down mathematically with sigma sigmas for summation and so on, so it looks a little bit more beautiful than it does here in the code, but essentially it's exactly the same. Okay, then another line of code which gives us the minimum from the Q matrix, or the Q dictionary rather, and this was also used already in previous code. It's really quite beautiful in Python. We can get out all of the items, so that means we get the keys and the values, and we tell the minimum function to sort by the second entry of those items. So they consist of key and value, and we're saying here sort by value. That gives us the minimal entry, and from that we're taking the first value because we have now pairs consisting out of a key and a value. We're not interested in the value, we're just interested in the key. So what min_q is doing here essentially, it's considering all of the entries in the Q matrix, is picking out the one that has the smallest value, but then forgets about that value and returns to us only the key, that is the ij that have minimal value in Q. Okay, then next we create an empty graph over here, and we fill it. Each of the nodes that we're considering is placed into this graph. There are no edges yet, they have to be connected. And then we go over the while loop. So while there are still nodes to be considered, while the length of all is greater than 1, we first of all print the matrix D, calculate Q, print Q onto the screen, get the two nodes A and B that have minimal Q value, and now here comes a complex calculation. So this is calculating the distance that we want in the tree from node A to the new node AB. So we will create a new node AB because we have decided that A and B go together. And we have to decide now in the tree what that distance should be. Now in hierarchical clustering we also did that, but we didn't really bother and we made it simply the half of the distance between A and B. But now we're handling it differently. We're also taking half of the distance between A and B, but we're balancing this now. So basically both of them get 1/2, but then depending on how they relate to the other nodes in the graph, we'll weigh them differently. So one will get shorter than this half, and the other one will get longer. So essentially you see this is all the same here. This is just a weighing factor. And the key is that this is UA minus UB and this is UB minus UA. And that is essentially the reason why in neighbor joining the branch length can be different. So we have decided A and B should be grouped together, so that means the node A and the node B can be removed from the list. So can the distance between A and B, and now we have to update all of the remaining nodes C that are still in the list. And we decide that the distance from the new node AB to C is equal to what the distance of A to C was before minus the distance that A has to the new node AB that we just calculated over here. We could have equally well also defined this to be the distance of B to C minus the distance of B to AB. Those values should be the same. You can easily verify that by inserting it into this formula into here. Then the distance from A to C and B to C are removed, which only makes sense because we removed the nodes A and B. The new node AB is added to our list all, so we have removed 2 nodes over here, we have added 1 node, so that means in sum 1 node was removed from the list overall. Now we add this new node to our graph, over here, AB, and two edges, from AB to A, from AB to B, and we use the lengths that we calculated. Then final 3 lines, we draw the graph and display it on the screen. So let's see what is happening if I press play. It's calculating. Scroll down a little bit. And bingo, there we go. Okay, matrix D, let's have a quick look. We see, for example, A to C has a distance of 7, C to B a distance of 8, pretty close to each other, D to C distance of 67, and so on. Matrix Q is being calculated, and let's see what the smallest value is. It's over here, A to B at minus 144. Interestingly, C to D also has minus 144. So A to C is actually picked. Oh, sorry, no, the smallest value is 168. So A to C is picked. And the distance matrix D is updated. Matrix Q is recalculated. Matrix D is updated. And then we can look at the final Q matrix and the final tree. So AC got joined, B and D, and the distances were not all equal. Let's just look. Again, AC and BD, AC and B to D, and that was the final result over here.